Please welcome Chief Technology Officer for Bristol Center for Supercomputing, Sadaf Alam.
Thank you. Welcome to the first invited talk session of the conference. It's my pleasure to introduce the first speaker for the session, Dr. Alonso Vera, who is the NASA Senior Scientist for Distributed Collaborative System. He has worked at NASA, okay, it's good? Yeah. Since 2000 and serves as Chief of the Human Systems Integration Division from 2010 to 2023. Alonso has cross-disciplinary expertise in human performance and human-computer interaction and artificial intelligence, and he has led the development of software systems across NASA robotics and human spaceflight mission, including Mars rover exploration, Phoenix Mars lander, Mars Science Laboratory, Space Shuttle, and International Space Station and exploration systems. With that, I'll hand over.
Thank you. So just to start, one of the questions that we're asked often as NASA people generally, but I get asked especially when I talk about this, is because I'm going to tell you a story that basically says that going to Mars is very, very difficult. And in fact, I think that we would not be in a position to consider going to Mars with humans were it not for the place we're at right now historically in terms of AI and HPC, and in particular, AI in the current form that it has, right? So that is basically, what I'm going to communicate. That 15 years ago, going to Mars really was out of the question and there are many challenges, but there's one big one that's a bit invisible, which is the one I'm going to talk about. So the question that we get asked is, if it's so hard to send humans to Mars, why do we do it? And there are a lot of good answers to that question, but the one I think that's particularly relevant here is because these kinds of missions drive technologies. They drive technologies to new applications, and they drive integration of new technologies in ways that we wouldn't have necessarily even pushed to do before, and those then become useful in other contexts. So that's, I think, the primary goal here is to talk about some of the areas that need to come together to enable this over the coming decade or two as we work toward a mission to Mars. So in 1948 or so, Dr. Wernher von Braun wrote a book called The Mars Project, where he basically said, we are ready to go to Mars. We can go to Mars. That book, then published in English in 52, was basically a set of equations for the trajectories and the orbital dynamics and so forth of that voyage to Mars. And really that's almost the entirety of the book, right? So the view was that we can get things to Mars, and that is true, and it has been true for decades now, right? So we successfully landed the first robot on Mars in the mid-70s, Viking 1. And Pathfinder was the first rover in the 90s. And then since then, we've been landing bigger and bigger assets on Mars and doing really more and more impressive science. We met with SpaceX recently, and they're planning to send a Starship to Mars, empty, right? And just head in the direction of Mars. We've been able to do this for the last 50 years. And I mean we humans, right? And so sending things to Mars is not hard, in part because, and I don't know how many of you are aware of this, when you send something to Mars, as we have done so far, it is basically off. It is a bowling ball on its way to Mars, right? So every now and then you may turn on the computer on board, maybe update some software, and it continues. So this challenge of going to Mars now with humans is a whole different ballgame. So The interesting thing about this quote, and in fact there are about 3 things that are interesting. So one is, he said, "It is time to explode once and for all the theory of a solitary space rocket." And this, you can imagine that kind of 1950s movies, and if you go back to Flash Gordon and all that, back from this period, that was the idea, right? That you just kind of fly around space. So he says, solitary space rocket and its little band of bold interplanetary adventurers. It was learned thoroughly how some ridiculously insignificant incident can jeopardize the results of years of preparation. And then he goes on to say, about a page later, and this is right at the beginning, the study will deal with a flotilla of 10 space vessels manned by not less than 70 men. A few interesting things. One is that ridiculously insignificant incident is, he was aware of that, right? That we're very good engineers, but we're not perfect engineers, so there will be things that you miss. There will be things that you didn't think of in the design process that you don't have, you're not prepared for. You don't have a procedure for, maybe you don't have software for it, you don't have the tools for it, right? And those things can cost you your mission. And part of the question is, how often does that kind of thing happen? The second, I think, really interesting thing in this quote is that number 70, and I'll come back to that. It's important. And part of, in that very first chapter, he talks about Columbus and the Nina and the Pinta and the Santa Maria, right? 3 ships. On one they can make sails, on another one they can make masts. So they had this notion of redundancy, et cetera. And that was the plan. And I think that if we could send a crew of 70, if we could do 10 vehicles, and really the challenge is, the expense of that would be just so enormous, right? As it is a huge challenge. But, that was the vision. At this point, we're trying to see, can we send 4, 6, maybe 8, right? But not much more than that, right? Because then you start getting into multiple vehicles, et cetera, and that makes it hard in its own way. So if we're going to send 4, what are we trying to put on board to enable that crew to make it there alive? So that's what I'm going to discuss. So first, spend a bit of time talking about managing expedition risk kind of broadly, right? Because the first question we asked was, have we solved this on Earth? Have we in the past, in different contexts, actually addressed this already? This is a picture from one of the expeditions to the Mariana Trench, right? The deepest part of any ocean on Earth. And so here you had a small crew. It's very risky. There is no evacuation once you're down there. You basically have a vehicle that's keeping you alive. It is a very hostile environment, right? It is high pressure, water, so you can't breathe, et cetera, right? So that thing is keeping you alive. And so how do we do it in those cases? Well, the primary mitigation is length, right? So when we do very risky things, and they are, and you can't escape and you can't resupply, they tend to be short. This Mariana Trench is about an hour and a half. Okay, so very short. Everest, by the way, when you think about Everest, high mortality rate still. It's gotten better, but it's still 1 in 100. Everest, once you get to the highest base camp, it's hours. You're talking 12 to 20 hours, depending on how things go, before you're back at that base camp, right? So, and Everest is not as bad as this in terms of a hostile environment. It's a very hostile environment, but if something goes wrong, there are some ways out, but you can't be evacuated, no helicopters can fly that high, et cetera, right? Okay, what about other contexts? So aviation, we've gotten the number of pilots on airplanes down, and they're flying the planes, and again, they can evacuate, right? So planes can land very quickly all over the planet. We've kind of set up the system that way. Also, if something goes wrong, you immediately start getting help from the ground, right? Clearing out airports and redirecting traffic, helping you with the situation that you have, right? So that's another mitigation that we have, is we throw resources that are not on board at the problem, especially when you need it, right? So we manage this sort of web of support for systems where we're trying to reduce the number of crew, say 2 pilots in this case. Space shuttle was similar, right? So the longest space shuttle mission was 17 days. It was maintained on Earth. In fact, if anything really broke of significance on or didn't work on the space shuttle, you waited till you got back to Earth, and you might lose part of your science experiments, or maybe you were going to deploy a satellite and you can't do it. But again, you had a lot of support on the ground. So short mission. If you're going to have a small crew, like here, typically the crew is 6, something in that order, right? And then you can get out of it. Space station has been up there for now almost 25 years, and obviously it grew over time as it was built out. So that's a long mission, but we've gotten to the point now where we can resupply it. So before we go fix something, we send up a whole new unit, and then we take the unit that's on board out, and we put in the new one, and we send the other one back to Earth. We have ways to evacuate quickly. And the support team on the ground is a significant size. And space station, and I don't know how many of you are sort of aware of this, but it is flown from the ground, right? So space station is commanded from the ground. All the troubleshooting is done from the ground. Often astronauts, and by the way, this isn't to say that the astronaut job is easy, right? They're involved, they're doing things, but really the bulk of the expertise in terms of troubleshooting, et cetera, is on the ground, okay? So these are the mitigations, right? So expertise and person hours, okay? So we can either throw a lot of people at it, or we can, either right there on board or, right there on board and supporting people. So real-time support, escape and resupply, and mission duration. Those are kind of the variables that we play with high-risk missions. So one of the closest ones, and by the way, in all this, we spent like 2 years talking to submariners. We talked to people in oil rigs in the North Sea. We talked to the people who winter in Antarctica. So we kind of went through all this. This isn't just kind of Wikipedia research. Attack submarines are interesting, right? Those are the ones that go down for 6 months, radio silence for 6 months. They tend to bring down everything they need, right? So, and it's often paper because they don't care that much about mass. So like we care a lot about mass. They don't care that much about mass. They have about 140, 150 sailors on the attack submarines. Half of them are doing the mission, right? So, radar and whatever else, cleaning the missiles, and the other half are keeping the submarine alive, right? So you have people who are doing the hydraulics and pumps and fluids. You have people who are doing the electronics, the IT, the nuclear side. And they're working in 3 shifts, 24 hours a day, okay, to just basically maintain the submarine, 70 or so, right? And so like I said, and so 70 is an interesting number, and that, so it was, von Braun kind of said it, and you might think it was a guess, maybe it was a guess, but it's come up again as we've talked to people about kind of how many people roughly you have to bring to bear when you have a complex machine and you're trying to keep it alive that's keeping you alive. Maybe the closest analog is not now, but it's in the past, right? So this is the Amundsen expedition to the South Pole, 1911. It was about 2 months long, so not as long as one of our missions. I'll say that in a sec. But there was no communication, no rescue, no resupply, right? There was no, they weren't leaving things along the way, right? So whatever you had with you, that is what you were going to have, right? And Amundsen and his team made it. There was a parallel mission, British mission led by Robert Falcon Scott, and they all perished. Interesting lessons in that I won't go into for the sake of time, but it is an interesting story. So again, very high risk, right? They were going in. There was no rescue, et cetera. Hostile environment. Again, not as hostile as ours. In other words, like you're in a vacuum. No temperature, no pressure, everything. It'll kill you right away, right? So, for perspective here, in terms of coming back now to what we're looking at in terms of Mars. low Earth orbit, space station is about 200 miles up. It takes about 8 minutes for a rocket to get up to low Earth orbit. It's now, as we've seen, it's now commercialized. NASA's job is to pave the way to make it, and so, once low Earth orbit was easily doable, you hand that off to industry. So now industry's, having, the resupply missions and, delivering astronauts and bringing astronauts back. So 200 miles. The moon, about 200,000 miles. Harder, 3 days to get there. The landings were difficult, and obviously the return and the docking, a lot more operations. Mars is 200 million miles away. Okay, so that causes a whole set of new problems, okay? And in particular, so I'll go through just, kind of the 3 key ones. One is, it takes about 9 months to get there. It could be faster if we develop new engine technologies, and there are Vasmir engines, which are ion propulsion engines, nuclear engines are under development, so it's possible that we will have better engine technologies. But right now we still have chemical fuels, and so you are basically going, everything in space at the moment is going about 17,000 miles an hour, because that is the speed at which you break out of Earth's gravity well. And so once you're off at 17,000 miles an hour wherever you go. So at that, it would take 9 months. And picture, and this will help you understand why some of this is hard. Earth is an inner orbit to Mars. So Earth is moving, Kepler's law a little, comes up on Mars and moves a little faster in its inner orbit. And so we launch when Earth is catching up with Mars, so to speak. And then, Earth keeps moving, right? So you're on a trajectory to Mars as Earth moves away. By the time you hit 9 months, Mars and Earth are almost at opposition on different sides of the sun. It's a very, evacuation and resupply are very difficult in this case. Evacuation, after 3 to 4 weeks of leaving Earth, it'll take you a year to get back, okay? Why is that? It's because Earth has moved away from you. And so what you do is you'd have to come back and wait for Earth to come back around and kind of come meet Earth again in its orbit, right? So after about a month of that trip, there is no evacuation. Resupply is also very hard. You're on a trajectory to Mars at 17,000 miles an hour. There's nothing stable about any point in between. If you put something, it'd have to be also going 17,000 miles an hour, which means you sent it at the same time. So there's no, let's put a whole bunch of stuff in the middle just in case they need more apples or pumps or whatever, right? And then the big challenge from our perspective here, right? Because again, we know that if you have a whole team helping, that this helps a lot. And so the big challenge is that your communication delay ends up growing to one way about 20 minutes. And it happens quite quickly, again, because Earth is moving away. It's not linear, right? So very quickly your communication with Earth is growing, and it grows to 20 minutes one way. So you have a problem on board, you send a message back to Earth, or maybe Earth gets the telemetry directly, and you can expect to hear 40-some minutes later, yep, like we're on it, and and then sometime after that, maybe that they're working the problem. Nobody at this point thinks that they're going to be commanding the vehicle. It's too much time. The comm delay is too long to be able to command the vehicle directly. So there will be a need to do much of the work that has been done by 70 or so people on the ground on board. The mission itself, in the end, ends up being in the order of 2 to 3 years, because there's a 2-year mission where you go, you land, you're down there about 2 weeks, go back up into orbit, come back. And then there's another one where you stay for a full other rotation and then come back. So long missions, again, with all this continuous comm delay. There's also a blackout of communication potentially, that when Earth and Mars are at opposite sides of the sun, opposition. A lot of people worry about that because it's 2 weeks, but that can generally be mitigated by reducing the complexity of operations, right? It's like, during these 2 weeks, don't plug in the microwave, don't do anything, right? So you can plan. The thing with the 20 minutes one way, 40 minutes, is just this continuous delay that prevents the ground from being able to do like the way that we've always done it, and to help in real time. And the real time aspect of this is really at the heart of it, right? Is how do we bring to bear this help in real time? For low Earth orbit, the communication delay is minimal. Even for the moon, it's a second and a half, so one way. So this hasn't been a problem. So our key question is, how do you put this expertise and person hours, and I'll give you a sense of the magnitude of that, on board with the assumption that we're still going to have 4 crew members. So let me say a few words about anomalies, right? Because none of this would be a big problem if we thought, well, bad things won't happen. But the problem is anomalies, which, basically an unintended or off-nominal state in a vehicle system. Anomalies happen all the time. So basically, pretty much every day there are anomalies. And a lot of them are not a big deal. They're things that have happened before. But every now and then, they're big anomalies. And the question is how much every now and then. I'll go through that data. But especially, we're interested in the anomalies that affect critical systems. And what are your most critical systems? So by definition, they are the environmental control and life support systems. And so very often, the critical anomalies are to those, right? Because those have the shortest time to affect. Those are the ones that will impact the crew the fastest if you don't take care of it. And then the crew won't be able to maybe take care of the situation. Power systems, also in some of the structured and mechanical systems, but really it's the environmental control and power systems. Depleted essentials, so if you can't resupply, right now, we can actually be venting atmosphere. And in fact, the space station is venting atmosphere. Like, as a public, you can go look at it. But periodically just bring up more air. We don't do 100% kind of recycling of water on board right now, but we'll need to, right? So any anomaly that happens where you lose one of these, you lose some water, or you lose some air, or you lose any of your fuels, is a problem. And then anything involving uncertainty. In other words, we don't know what this is. And there are a few varieties of that. Some of them are more involved than others, which is interesting. So one variety of that is that there's an anomaly, and I just don't understand why it's, are we really leaking this here, or is this, is it a problem somewhere else? Is it in a chip, right? So sometimes you don't know the source. Lots of other cases, you know what's happening, but it happens a little differently every time, and therefore how you respond to it is different every time. So you have to generate procedures on board to respond to situations that you, again, it's not a mystery why it's happening, but what do I turn off in order to save power for 17 minutes kind of thing, right? So we've done a lot of work on the International Space Station to just characterize how often these kind of things happen, how we respond to them, okay? The data I'm going to show you for the space station are very conservative, right? So this is interesting. So we didn't include EVAs, right? So when the astronauts are outside the space station, because too many things go wrong. Like, things go wrong all the time, right? So that really, we found up the numbers. Anything that was a more kind of complex, involved operation, we didn't include. We just said, for normal space station going around, how often do problems happen? So what we found, and this is through about 2019, so 2000 to 2019, along the bottom axis. And for export control reasons, we had to, it's not that I forgot to put the dates. There were some things that, so we looked in particular here at what are called high priority items for investigation, which is when something happens, they're called IFIs, right? Item for investigation. And it's when you're not sure what it is. High priority ones are ones that affect a critical system that are not anticipated and that require diagnosis. We found there were 68 of those over that period, 19 years. 36 of them really required immediate response, urgent response, and that when we looked at them, very well could have ended up badly were it not for the response from the ground. So they kind of a genuine anomaly that could have had a loss of crew, loss of mission. That averages out to 1.7 a year, and you can see that at the beginning of the mission, that's almost double. And that's always true in physical engineered systems, right? You have this bathtub effect, and at the beginning, as you're getting to know your vehicle and you're getting the kinks out and you're discovering a lot of the design issues and manufacturing issues, you have more issues. And then you see it level out, and then it's bathtub effect because things start aging out at the other end and as you begin to work toward retiring the asset. So the first 4, 5, 6 years, it was close to 4 times a year that you had a really big event that was like a threat to the crew or the vehicle or the mission. Just as interesting, this is a different analysis that we did. There are alarms and alerts. A class 1 alarm is a fire, a rapid depressurization, or something toxic in the cabin. You don't try to figure that out. You just safe yourself. So the crew just goes and saves themselves. One level below that are class 2 alarms, and those are that you have a situation that needs to be dealt with immediately by crew or ground, to avoid injury or death or damage to the vehicle. Okay, so now those, an average of 28 times a year. If you spread it out, it'd be like, every 12 days you have an alarm telling you might die, right? And what's interesting about that is, in some ways, that's the real number that you have to respond to, because the crew don't have to respond to those. A whole bunch of people on the ground say, no, it's okay, don't worry about it, we got it, and So that is and NASA, we hadn't done this sort of analysis before to say how often does this happen? How often do we have these kind of problems? Just on average. And then, I won't present this at all, but we looked at nuclear power plants, at trains, again, aviation, civil and DoD space flight. In general, this holds. You have rates of engineering failures, anomalies that are really quite proportional to the operational complexity, and that just they won't go away, right? You get better at it, you decrease it, but they don't entirely go away. For Apollo, we looked at it too. Apollo, we all know Apollo 13, but just as an example, Apollo 12 was hit by lightning on the way up, and basically reset all of its electronics in those minutes. And every mission, there was an average, I think maybe Apollo 17 was the cleanest mission in terms of like not having a big deal, but in general, they had problems on every mission, big ones, right? That in some cases cost mission goals, but they were of high risk. Okay, so our goal there was just to establish, okay, yes, 9 months to Mars, and then really a 2 or 3 year mission is probably not survivable without the ground being able to help. Okay, and I say that, and I say it that way because sometimes people say, well, we know Mars is risky and we're going to have to accept more risk. And you say, well, are we going to accept a risk of like 100% of a bad outcome, right, on the way there, right? So I think it's helpful that way, right? So, and here's like a really important thing that we kind of discovered by accident. In 2013, there was a study done by the NTSB on aviation incidents and accidents, and they found that 40% of the root cause in the end was something that was not thought about in the design process. 40%. Okay, so that, and when I first saw that it stayed in my head, right? So, and I know this is, the researchers who did that work. And then in 2023, 10 years later, the NASA software fellow at the NASA Engineering and Safety Center did a study, and she found that 40%, that same number of software issues across all space flight, 40% were unanticipated. In other words, you didn't have code there, so that right there tells you, like our old rule-based AI, digital twin, all of these where what's involved is us putting into these systems what we know, they're going to get you to about 60%. And the 40% of stuff that you didn't think of is not going to go into any of your models. It's not going to go into your rules, into your procedures, right? So that became the gap that we were interested in. And that's why I say that really it's the transformer development that has changed our ability to deal with this. And I think you can probably imagine how, right? Finding patterns in the data that you didn't think of. So our ground response capability, I'll go through this quickly, but look at that top number, right? You have about 70 controllers. This is how, we went and we counted. We were a little surprised by this ourselves. We're like, 70. Around the clock, so, in 3 shifts. And then, I won't go through it, but a lot of expertise, right? You see, the number of degrees, the types of, degrees being in terms of education, the number of years of cumulative experience. So that is how we do it. A lot of human expertise in the room, and having been there a number of times as part of that, it works. And we've been actually very successful in keeping the safety at a level that's been acceptable. About 1,100 flight investigation teams assembled over the last 24 years. I mean, think about that, right? Like in a flight investigation team is you bring that together when you have a problem you need to work on. About 100 anomaly resolution teams. Anomalies are then a bigger deal. So basically what we've learned to do is to manage it in part through training of the ground controllers. It's almost, people say becoming a ground controller is kind of like getting a PhD, right? It's a 3-4 year process, right? And you get very good at it. Importantly, we also have a huge amount of engineering analysis, right? So we have all this documentation, like the problem report history, right? Every problem that's happened, you have it in the problem report systems. You have all your history of tests, all your failure modes and effects analysis, your hazards analysis. We have this just huge amount and your drawings, and none of that is particularly well put together. And I suspect that that's actually generally true. It's a challenge to, then you get model-based systems engineering, which might help, but has a high cost, right? So you have all this engineering data, and then you got your human expertise, and that's how we've done it so far, right? So mitigating the risk of a ridiculously insignificant incident, to go back to the Wernher von Braun quote, right? So how do we do that? So the way we've done it, right, is we've got our engineering and operations expertise. Again, our 70 people, all that training, all the documentation, all our drawings, and I was sitting there for one mission where one of the thermal blankets had lifted on the space shuttle, and they were like, "What's under that?" It was on one of the back engines, and it was about 2 inch by 2 inch. It took about 24 hours for them to figure out what was under that. Okay, and why? Because those blankets get put on at the end, and so they're not precise, and so you don't have perfect drawings, and all this remains true of how we engineer these complex systems. And I'm spending a bit of time on this, the kind of the complexity of human engineered systems, because even where we are today in AI, it's not something that's still easily amenable, right? It doesn't have a syntax like protein folding has a syntax, and coding has a syntax, and language has a syntax. It is a different kind of analysis, and that is what we're working on. So right now, we've got all that engineering and operations expertise codified in documentation, and then you got your 70 flight controllers. Well, like I was just saying, so we have machine learning now coming up, and that does change. It helps maybe with that 40%, right? So, and the other thing that's really improved dramatically over the last decade plus is sensor technologies. Why? Because all of a sudden the value of data has increased so much. So real world sensors have changed incredibly, right? So low power, no power, very low mass, very modular. So we're investing in that. But the other thing that I want to mention are current data sources to do this work. And so we've got the ISS historical data. All the ISS telemetry that has been sent down to Earth is available, and we have access to it, and that's what we've been working with. We're also developing and using current, and like I said, developing analog hardware. So At Marshall Space Flight Center in Huntsville, we've got a set of the environmental control systems that are there for testing, and we're working with those. You can get data off those. And then we're developing software simulations, especially if we want to look at environments where you've got much more data than we have now. We had a really interesting lesson learned as a group a year ago. We were at Daytona Beach before the 24-hour race, and they told us that every one of those vehicles is throwing off now I can't remember if it was 5x or 50x, but the amount of data, it was 50x, the amount of data that it was 5 years before. So a 10x per year number of sensor increase on those vehicles. And we care as much about, they care about mass as much as we do. So we're very aware that, that the amount of data and then the amount of computing that we're going to have to do at the edge. And by the way, I've really appreciated being here at the talks and discussions that I've been able to take part in, because it has put into perspective a lot of what's happening in that area. I also attended a self-driving car meeting earlier this year, which was also very instructive in terms of just how much computing is happening at the edge and how fast that's growing, which is good. Although we need to put it all on radiation-tolerant chips, which is a whole different problem, which is progressing slowly. So just give you a bit of the flavor in the last couple of minutes here. We started out focusing on the power systems. The power systems are interesting because they're a bit like the circulatory system in biological systems, where the power systems carry information, the circulatory system carries information about the systems that it touches, right? So if you go and get blood drawn, it'll tell you about your endocrine system, it'll tell you about your blood sugars, it'll tell you whether, how your monocytes are doing, do you maybe have an infection that you're fighting, right? So you can get all sorts of information from testing your blood. Power systems in any complex engineered system carry information about everything they touch, right? So that first diagram on the left is basically capturing the noise, the very noisy current through a transistor of about 9 different systems that are being fed by that circuit. The first effort is to then isolate those, and it's interesting. You let machine learning run on those, and of course, quite quickly you are able to disentangle the 9 systems because they each have distinct kind of patterns. And then the key, and this is what we then try to pull out. We pull out one. For example, we're very focused on the urine processing assembly. So, it's true. You take the urine, you process it, you get water back out, and so. But it's one of the critical systems, and it has a lot of issues. It's had a lot of issues recently. And so in blue there, you're seeing the urine processing assembly. And then we start looking for patterns that anticipate, patterns in the power system that might anticipate, for example, or if not anticipate, if a fault happens, tell you, the fault is here. So it could be real time or it could be anticipatory, and finding those patterns through the power system, as well as covariation, especially covariation over different time periods, right? So that's something that's actually quite hard, and it's hard for humans to, and controllers to, this happens, but every couple of weeks or a couple of months, right? To detect those kind of patterns is hard, but that's exactly what obviously we're able to do well with machine learning. So we're advancing quickly here. One of the key challenges that we're having, though, is that, and I've heard this for today, and the conversations we had yesterday. Real time remains difficult, right? So one of the things that I think needs to happen is we need to move toward real time input from humans, but then also maybe from your engineering data, et cetera, into the model, into your foundation model, to change that foundation model in real time. Okay, so not just sort of the surface interaction where I'm not changing it, right? And I can give you examples of that, but it's something that we humans do, right? If I learn something new, and it's important, I will change my model. It doesn't just stay in working memory, and that is something that we're not being able to do right now, is to make that change, right? And so, and again, it's something that we do, right? If I learn something new, my wife would argue I don't, but I think that, so how do we, in our models, change something based on, say, for example, crew input? Crew as either a sensor. Crews are good at saying it smells more smoky over here, or crew as a generator of a different possibility, reporting something that the system's not aware of, context, for example. And then, yeah, same thing with the system, with the engineering data, right? So you get something back, and it would be great to have, like, the engineering data say, like, yeah, that was replaced yesterday, and to have that knowledge be in there and kind of reweigh things, right? So, and then, like I said, crew interaction, and we're doing a lot of work, and this is the last thing I'll say, and then I'll stop. That basically, and this is an interesting thing from our field, every time we go out and we look at any complex problem like this, the interfaces for the humans are terrible. So even at Daytona, right, where, I mean, you know, the cars are unbelievable. Like I said, the data, the technology was incredible. We got there behind the, you know, in the pit, and you're looking at those interfaces, and they're as bad as ours in mission control, right? You know, they're looking at raw telemetry. So I asked, and they said, well, you know, these people are really experts. And so the key is, if you can throw humans at it, you will. So the idea of kind of trying to kind of compact information and pull it up and provide context so that a human can, like, work with it is something that's also a somewhat untouched problem, interestingly, and that's, you know, more on the other side. So we're working on that too, and we've got, at the moment, 7 flight controllers working on our team, so active flight controllers on Space Station program. You know, and then let me just, basically our goal here is to demonstrate that unanticipated patterns in telemetry can be identified and integrated with existing engineering analysis, and presenting the situation awareness, decision support, and procedures to crew in real time, and that real crew and our engineering data can work back with it. And so, like I said, 2 high-level challenges, both of them about real time. One is, you know, the crew input, and the other one is the foundation model being able to be worked in real time to change its assumptions, right? So those are the things that we're focusing on. So again, my goal was here to give you a picture of a problem that hopefully is interesting, and be happy to have questions if there are any.
Let's first thing this. Thank you. Is this one on? Okay. So if you would like to ask a question, please use one of those microphones. I think that they are lighted, so that people who are online could also hear you. And I'm watching the online. So any quick questions to start? Okay, so while we are waiting for people to start questions, so for me, I mean, it's fascinating. I mean, there is just so much going on. You just don't. So if I look at it from this point of view, do you think there is a lot of, like, if you design complex engineering system where humans are involved and their lives are at risk, you think there is a lot of commonality from your analysis and understanding and comparing the system that we could use for a mission to Mars, or do we have to just completely rethink
the systems themselves, in terms of, yeah. There are things I think, you know, we need to rethink, and I think that, so part of our goal is to bring data forward that would basically drive some rethinking of the engineering, and maybe the main one is sensors, right? So not just NASA, but across the across aerospace, you know, companies and you know, DoD. Heritage is a big thing. So we've been doing sensors the same way for a long time. And it's mass and it's power. And so we worry about putting more sensors cost us a lot. So there's always a lot of thinking about sensors. And I think the sensor world has changed around us. And I think that, you know, the way to make that change is for it to become very clear that that all that data is of high value in terms of this, right? And again, you don't need it if you can throw 70 people at it. But if you're trying to reduce the number of people, which, again, is kind of the underlying theme of what we're doing in AI, and if you're really trying to do it for these kind of complex problems, then we're going to have to rethink sensors, among other things. But yeah, the problem of heritage in space systems is it's a big challenge.
So we have time for one quick question because we would like to start. So if you could ask away very quickly, and then we go to the next session. Yeah.
Hello.
Hi.
Thank you for this amazing talk. I am really fascinated by space, and I was really interested in knowing what is the future perspectives now on the manned mission to Mars. If NASA is waiting on improvements in HPC that we see in this conference, there are so many, and improvements in AI, or if there is already a time frame for this manned mission that you've been announcing here.
No, so some of these improvements, certainly in HPC, but even in AI, they have to, like we're already bumping into performance issues with the kind of analysis that we're doing now, right? And the scale of it is minimal compared to what really will have to be done, right? So we're looking at the power systems relative, like I said, to the urine processing assembly. And so we're talking about a few thousand sensors, right? So we know scale is going to be a big issue, and then the onboard computation is going to be a big issue, and AI as well, right? So obviously, most of our documentation is not really written in English; it's written in engineering, right? And so what do you? It's a harder problem, and so there are aspects of it. And I take to heart, for example, the opening plenary this morning, right? That we're going to see real advances, and I think we will. The belief system, whether you think AGI is really coming or not, but I think that advancing the ability to pull data out of existing repositories is a critical thing too.
So we are not ready yet.
We're not ready yet, right? And that's it, and it's interesting, right? Because again, we can send things to Mars, right? And SpaceX may send something to Mars, but again, without humans in it, it's a different problem. And but as I said at the beginning, and I think the key to this is that these kind of problems then drive getting ready for this, and then result in technologies that I think are relevant and valuable elsewhere.
Thank you.
Okay, thanks so much for such an interesting conversation. Okay. I was waiting for a music sort of thing. Sorry. It's my pleasure to welcome Professor Aldo Faisal from Imperial College, who's Professor of AI and Neuroscience at Imperial College London, and he's founding director of a £20 million UK Research Council. It's a center of doctoral training in AI for healthcare at Imperial College London. His own research labs are the Behavior Analytics Lab at the Imperial College Data Science Institute and the Brain and Behavior Lab at the Department of Bioengineering and Department of Computing. He's also chair of digital health and the University of Bayreuth. I will probably pronounce it. Yeah, and Aldo's expertise lies in combining data-driven method, machine learning, and human behavior and neuroscience to develop a novel human-aware AI technology that helps people in health and disease. With that.
Thank you very much. And thank you very much for inviting me. So I'm a professor in London. I'm also a professor in Germany. And I've been working on models and AI systems for healthcare. And I've been so long in AI that when I was younger myself, I tried to avoid to say that I work on AI because that was a bad word in those days, and I was doing machine learning. And we are working on machine learning for healthcare. And I want to talk to you about our current effort, which we call Nightingale AI, which is to build a health foundation model at a nation-state scale. And this journey, and the next slide, please, because this one is not working. Thank you very much. Starts, of course, with history. So about 150 years ago, we had major public health problems in the world. And in the beautiful city of London, where I'm from, we had Jon Snow, who knew nothing about cholera, but he had to deal with a cholera epidemic. And in those days, We didn't know whether cholera was coming from a disease that's borne by an agent, bacteria were not yet discovered, or whether it was coming from bad air, so-called miasma. And so John Snow did a number of things. He was a medical doctor, and he was very empirically minded. So he drew out the number of cases you could find of cholera in central London, and this is the very central part of London near Covent Garden. And he had this crazy idea of drawing a thin line for every person who was sick with cholera in a given house. And so basically, the more people were sick, the higher he stacked these little black lines, and he thus invented the bar chart, beautifully visualized in this first showing of a bar chart in human history. And you can clearly see that the data is nicely clustered around the center of the picture I picked. And at the very center of that picture is a water pump. And that water pump you can still see today in London. It's the water pump that's located there in Broad Street. And he had a suspicion, because the data was clustered around there, that you could, so to speak, link it or correlate it with cholera as a disease. So this was a generative model, as we call it now. He presumed the data was generated by the source, so the data being, of course, the cholera cases, and he ran this model, so to speak, in his head because he didn't have better computational methods. Now, the intervention that he derived from there was to shut down this water pump, and lo and behold, within a few days, no new cholera cases were identified, and basically he stopped the pandemic through that intervention. And so from there, he invented epidemiology in the modern sense. He established a link that water is the disease-carrying agent in cholera, and he basically invented medical data science. And so this takes us to the present day. When we're talking about AI in healthcare, we're walking on these steps that John Snow started in those days. And of course, when we're asking, why do we need AI for healthcare, then our goal, my goal, is not to replace nurses and doctors, of which we don't have enough anyway, but to try to tackle the rising unmet demand for health and care. Unmet due to cost, unmet due to staffing issues, unmet simply because we have a lot more demand. If you saw the keynote this morning, you see that we have this tombstone-like age structure. We're getting very quickly very older, virtually almost on every continent on this planet. And so the idea of ours is to use AI to reduce the unmet demand for health and care. And of course, when we're talking about demand, we're talking on the one side about AI, and AI is composed to me out of two components. One is data, but AI is of course a lot more than just data science and data engineering. It's about agency, enabling systems to do stuff. And we've seen what generative AI can do. We're approaching the year or 2 or 3 years in which we're talking about agentic AI, because before we're approaching the stage of recursive AI, where you have AI systems improving AI outcomes. So what's the biomedical case that AI can potentially deliver? And this is basically all quotes of solutions that AI can offer. So we know that life expectancy is stalling worldwide, and health inequalities are widening. In the US, life expectancy has been actually going down in the last few years. And so it's been estimated that AI can boost life expectancy by integrating healthcare services by over 1.4 years, just using existing AI systems, and reduce inequalities by understanding and monitoring these services. We know that key risk factors are driving a significant and unequal burden of preventable ill health. Being overweight, being obese, having bad nutritional patterns, for example, can lead to premature death. It has been suggested that AI Sherpa systems that guide you through the healthcare process can address over 1 in 8 preventable deaths and reduce emissions by over 50 to 90%, because you don't enter complicated or expensive care pathways that you don't need to, because you have acted early enough to prevent them. We also see that people are simply living longer with major health conditions. Up to 80% of emergency admissions to hospitals can now be predicted with AI systems up to 3 months ahead before they happen and can be technically prevented. We have an unmet need that is substantially increasing, and yet only 2/3 or less of the clinician's time is spent on actual care interaction with the patient. And it's been estimated that 25% of this unmet need is directly addressable by AI. And similarly, we see that due to lack of investments in a lot of healthcare systems, especially at the national scale level, you can use AI systems to introduce immediate savings that make healthcare more accessible and more affordable. And so if we're asking ourselves, what is the main challenge from a clinical perspective, you will see that clinicians simply complain that they are overworked and very often burn out. And there's been a beautiful study that happened on the East Coast where they had 2 wards of radiology, and in one ward, same hospital, same structure, they deployed an AI system that was used to support radiological diagnostics, and in the other they didn't. And they were able to show a 50% reduction in burnouts among medical doctors for the ward that had AI systems installed. So there's a very powerful case here why we should embrace AI and drive it forward in the case of healthcare. So if you ask yourselves, where are we on this journey? And I've just showed the journey of computer games from the very early Pong to the Atari system, some of us may have still played with, all the way to modern computer graphics games like The Witcher 4. Where are we on this scale? And if I ask you, and I've asked other audiences before where we are, most of you will probably say we're somewhere around EGA or VGA. Well, actually, I believe we're still in the Atari 2600 age because we're making so little use of the data and of the agency that AI systems can offer us in healthcare. So what are the challenges that we're seeing? Well, if you look at current AI, why are we not seeing more AI systems being actually deployed? You hear people giving talks about AI for healthcare, but you don't see them actually being deployed in hospitals or at your doctor's office. Well, there are a number of issues. If you really want to have patient-ready AI, you need AI systems that can overcome what we call the observability gap. The AI system needs to know how you're doing, even if you don't have current medical data flowing into it. The next challenge that we have is we need to overcome a treatment gap. So treatment is where the work of the clinician really starts in treating and prescribing you with the right treatment. Here, we have hardly any AI systems that have been developed. Most of them are still in the diagnostic domain. And finally, once you've developed an AI system that you can deploy in the healthcare world, you have a challenge that we call the translation gap. You need to bring this thing to market so a doctor or hospital can purchase a product and prescribe it to help a patient. And so you have a number of gaps that you need to address. So the first challenge that we have is that we need to have data. In Great Britain, we are very lucky in that we have what we call a national healthcare system, where all people are insured by automatically from birth, and we collect all data. It's the 3rd largest employer on the planet, and we have all data of all British people using this healthcare system. And so at the moment, there are a number of very large databases that have been generated. I've been involved in the Discover Now and One London effort, which brings together patients first from Northwest London, where my university is based. We're using 2.3 million patients, and it's been now ramped up to bring all 10.1 million patients' data from the Greater London area. And then in Wales, that's one of the 4 countries of the United Kingdom, we have since 2009 all citizens' medical data integrated. All general practitioners, all hospital data, all pharmaceutical data, and even the social care data has been integrated and linked. So these are really labs where we can think about developing AI systems that have a very comprehensive view of the patient and their trajectories. And a very exciting development that's coming now from Europe is the creation of what they call the European health data spaces. So it started officially in April this year, and by 2029, all healthcare data and healthcare-related data in the European Union must be made available for secondary use in an anonymized fashion for healthcare research and innovation. So in 2029, we'll have almost 500 million worth of patients' data coming online. And so the question is, what we do once we have data at that scale? So a few years ago, we became aware that we had this data in Wales. And so we asked us, can we build a Gen AI system that operates on a national scale and solves a very practical problem that you have in healthcare? So we didn't want to do a model that's based on a hospital where you do a lot of tests and a lot of analysis. We wanted to do something that works for a whole population. And so a big problem that you have these days is demand planning on hospitals. You need to know how many people are showing up in your accident and emergency unit, how many people are being unexpectedly taken to hospital because of a heart attack or a stroke. And so we asked ourselves, can we use the primary care data that we get from thousands of GP practices all around Wales to build a model that can learn to predict for every single citizen in the country whether they need to go to hospital unexpectedly in the next 3 months. And of course, the challenge here is you don't have a lot of data. There is an observability gap, right? You don't get a blood test every week. Maybe you don't see your GP for months on end. And so what we asked ourselves, if we have data at the scale of several million patients, can we build a model that allows us to extract from the most basic demographic information, age, gender, when they were born, where they were born, where they're living, and a metric that we call the measure of social deprivation of their postcode where they're living, together with a simple live data element. And that is what we call the timestamps in your electronic patient record. So we ignore what you have. We ignore what drugs you're taking. We ignore what treatments you're getting. We ignore whether you went to hospital. We're just looking at the timestamps in the time series of the data that we get from your electronic patient record. And so with these 6 demographic numbers, age, gender, and so forth, and the timestamp pattern, you can build and discover new features. And so effectively, what we've used the timestamps to train the machine to look for an unknown language, crack the code, an unknown Morse code of health. And indeed, we were able to discover patterns in the timestamps that allow us now to predict with over 81% accuracy if an individual needs to go to hospital within the next 3 months. We trained the model on 1 million citizens. We tested it on another million, and then we tested it again on a second set of 1 million citizens, and we randomly shuffled whether they were from the countryside or from the bigger cities in Wales. And so this model effectively uses very accessible healthcare data to deliver a solution that allows us now to predict at a national scale whether patients need to go to hospital. And this allows us to do 3 things. We can tell the hospitals what the demand they're going to have in the following week for the accident and emergency unit or for their intensive care unit, for example. Second, we can tell the doctors that are looking at patients and have patients maybe even on a waiting list whether they should prioritize certain patients or call back some patients. And ultimately, we're in discussions whether with the healthcare providers, whether we want to actually directly call out to the patients and very gently say, hey, why don't you go and see a doctor? You may have something that will take you unexpected to hospital in the near future. So this is just an example of what you can do once you have access to national scale data. Another example is another study that we've been running. This is the idea that medical relevant information is literally everywhere. And of course, you know that supermarkets collect all your shopping data, especially if you have loyalty cards. I think Safeways in this country does that. In the UK, Tesco was the first supermarket to do that. And so my colleagues, James Flanagan and our joint PhD student, Kevin Horo, we looked at this problem and looked at healthcare shopping baskets, and we collaborated with one of our university hospitals, that's the Royal Marsden Hospital, which works in cancer. And it's the top hospital in cancer in London. And we recruited women who were diagnosed with ovarian cancer. And ovarian cancer is very critical because the earlier you can diagnose it, the better you can treat it, like with most cancers. And so what we discovered there is that the onset of cancer very gently perturbs your shopping patterns. You buy different things because you don't feel like before. And again, using a very simple Gen AI model, we were able to extract signatures that are indicative of ovarian cancer onset 8 months before these women actually were diagnosed with ovarian cancer. So that was a retrospective analysis. And so now we're taking this idea forward and trying to incorporate with supermarkets and drugstore chains whether we can get more shopping data and use this information to build better predictors that patients can then use on their phone to extract their shopping information from different providers and then predict and inform them whether they should go and deal with a medical diagnostic or go and see a specialist. So what I'm showing you here are examples of what in the future we are most likely going to call holistic health. The idea that all the data that is being collected anyway about us and all the data that we can make available through us because we own or control that data, we can integrate that information and start making predictions about what happens to your health. But of course, if you have medical data, you know also what treatments were done to patients, so you can also learn how to intervene. And you can intervene by prescribing a drug, doing a surgery, or in the case of a lot of lifestyle diseases, you can think about behavioral interventions. You can think about ambient intervention. That's your house or your apartment telling you, hey, go to bed earlier, or why don't you move a bit more? Yeah. This would be possible if you had an AI that was multimodal and could digest and read the most diverse sets of healthcare data. And, well, how does this data look like? Well, we need to think about this data that is not necessarily language data. And so we want to build now, that's the motivation for Nightingale AI, a system that can read medical and biomedical information that's out there. So this is not about large language models in medicine. This is not ChatGPT doing things by asking it a medical question and then you get an answer. Yeah? To me, that's equivalent to asking someone who has a degree in English literature and has read a medical textbook to give me medical advice. That's a system, ChatGPT can answer you that with the expertise of somebody who knows a lot of language and has read a lot of stuff. It doesn't make you a medical doctor. So if you ask, for example, ChatGPT, what's the relationship between heart rate and blood pressure, it will more or less tell you it's a linear relationship. The higher your heart rate, the higher your blood pressure. If you actually look at the medical data, so the American Medical Association tells you, well, the relationship is not linear, it's nonlinear. Of course it must be. You can't have infinite heart rate, and you can't survive with a heart rate of 1. So these relationships are not captured if you're reasoning about text. So we need to start thinking about foundation models in medicine. And yet most of the efforts that you see in this history of foundation models, effectively since the first 2017 paper on transformers came out, were focused on language. Fortunately, we had developments where people started to think we need to actually benchmark medically these systems when we ask them about the health trajectory of patients. And there was a beautiful Nature paper that came out earlier this year where people started building models using just the disease codes in the trajectory of patients. And again, they used some of the data sets I outlined before to do that and could predict what future diseases you would get in 10, 20, 30 years. So that's great, but that's just using disease information. So is there a foundation model that can really deal and read all sorts of information? So these days, there's almost a foundation model for everything, right? It's a bit like in the previous days, Airbnb is the Uber for hotels, right? And we need to think about what we can actually do in this space. And so we've started doing a very systematic review and comparison of what's out there in terms of interpreting different forms of biosignals. And you can then extract standardized recipes by which you can build different forms of models, backbones, dealing with knowledge provision, so-called RAG, for example, building agents, thinking about multimodality. And this led us to formulate what we now call Nightingale AI. So Nightingale AI is named after Florence Nightingale, the nurse and reformer of the healthcare in the 19th century. And it's a foundation model that brings together electronic patient records, biomedical data such as genetic information, scientific literature, and other forms of information like the demographic information in this Morse code of timestamps, but also, for example, information like shopping data. And so we want to build this foundation model. And that's, of course, not just my research group. It's an effort of many institutions that are coming together. And the fundamental idea that we have behind it is that we want to think about Nightingale AI as something that can read all sorts of information as it appears. And so we're starting, for example, with the trajectory of a patient. He goes to a GP and gets a drug prescription. Then he's a medical assessment, an ECG is recorded. Then some point later, a referral letter is sent to him, and he goes to hospital for an X-ray. And then later, there's another medical assessment, and an ECG is taken again. So that's the form of data that we are observing in the real world. And so we're now going to take this patient's trajectory and transform it into a stream of tokens. So at the start of the patient data stream, there's the gender, age, ethnicity. Then we know, for example, that this patient had an emergency admission, so we have emergency admission as a token. And as the information flows further, you get a clinical node, a test result, another clinical node, and so forth. Right? In the world of language models, this would be simply words and sentences and paragraphs of text that you put into the model. In our case, there's no language in an explicit form. It's medical, biomedical, and scientific information that we're entering, and that this model needs to be able to digest, and each token may have a completely different modality. Let me show you the basic model. And so we launched Nightingale AI in March 2025, so just a few months ago. And so I'm showing you basically work that's ongoing that we developed over the last 6 months. We started with a simple transformer baseline where we had started just with hospital data. We started with the simplest possible data that we would start off because we had these sets already available. So you take a stream of EHR tokens, you pass it through a context window, you transform this token stream, and then you run this to a GPT model that basically predicts not the next word, like a language model, but predicts the next medical record. What's your next blood pressure if you take this drug? What's the next heart rate if you sleep? And so when you look at these token streams, you first of all realize that in the medical literature, there's a lot of things that we're recording. So on the right-hand side, you see the number of different tokens we have in our vocabulary. There are infinitely many things you can be sick of. That's why we have a lot of tokens diagnosed, relevant to diagnosis. There's a small set, relatively, we're still talking thousands of different lab tests that can be done to you. We have a small set of drugs that are typically prescribed to you. There's interesting, a larger set of different billing codes that are used to describe how you've been treated or how you've been diagnosed. And the actual range of values is actually very small in comparison to that. So with this simple model, we can then run this through hospital data that we have available, 60,000 patients worth of data and their entire journey in a hospital. And you can now see that, of course, we have a lot of values that were recorded, your blood pressure, your heart rate, and so forth. We have a lot of lab test results. We have a small range of diagnostic outcomes, an even smaller range of treatments, and a lot of different drugs were prescribed or their dosages changed. Just to give you a bit of feeling of how this data looked like. And then we can start building these models. And now, this is why I'm talking at an SC conference. This is not easily doable anymore on a set of workstation or on a simple cluster. We need to scale up. And so the first test that we need to run is, how big of a model, how many parameters do we need if we simply want to be able to digest hospital-type data? And so we very quickly found that our model, given the amount of data that we have, plateaus at roughly 100 million parameters. That's 14 layers deep of GPT-2 encoding that. And what's quite interesting is you can then pop open the hood of this model and compare that data to data that was obtained by the Nature paper I mentioned earlier, the Delphi 2 million model that just looks at disease codes. And you find that the representations in these are visualizations of how the model internally thinks about this medical data. Now, what's interesting thing is that the Nature model used only disease codes, and their only stream was the stream of disease codes. There was no time in between. There was just one disease after another. Say you became overweight, then you got diabetes, type 2, then you had a heart attack. So you had 3 disease codes coming in a row. Here we have all the data streams that you get when you're in hospital. All the blood pressure, heart rate, breathing rate, what was prescribed to you, what you took, whether you slept long, whether you were in an intensive care unit or not. And so you see already that we're capturing a lot of the diversity in this data, and we get similar representations to what you get with this simple published model. But now, when we're starting to talk about models at this scale, we really need to think about how we're evaluating this. And so we had the fortune, almost from day one, to partner with Isambard at Bristol University, and we needed to start thinking very differently in our experiences of how we were building model in our workstations and small GPU clusters. So first of all, we need to switch to a systematic way of evaluating models, architectures, and design. And of course, if you're one of the big 5 companies, you will have experienced that. But if you're in academia, you don't have access to systems that have 1,000+ GPUs available. And of course, you're realizing very quickly that failure of nodes, resets, end of runtimes become suddenly a critical factor in the way you design and build your training pipelines, and we had to learn that. So on Isambard, and there should be a video playing, we basically used roughly 75% of our compute time so far to run simulations of patients, roll out what may happen to this patient. 15% of our compute time was used to do model exploration, and just 10% of the time was used to train the models, where the largest model we built had 100 million plus parameters. And then we need to start talking about data. So one of the things that we started in parallel doing is build a coalition of hospitals and universities that wanted to provide us with medical data for research and development purposes, of course anonymized. And so very early on, we had partnerships from previous work that we've done with 3 of the big pediatric hospitals in London. And through connections, we were able to bring on board the Children's Hospital of Orange County, which is now merged into Rady Health and is the 3rd largest pediatric hospital provider in the US. And so with this data set, we are now basically assembled data that is as large as the largest hospital data set that's available in open source. And with that, we can now start applying AI to problems in pediatric care, not just in hospital care. Almost everyone does hospital care for adults because there's tons of data. But if you think about it, there are very few people between 1 and 3 years of age compared to people 18 to 65. So that's an underserved community. And so here, I'm just showing you how different the data looks like. I show you just the heart rate in the data of patients that are under 18. You can see how very different that distribution of heart rate data looks like to the data of adult hospitals. And so we had to develop pipelines for ingesting and translating and editing this data. And of course, again, we started using generative AI models to try to automate this ingestion process, because once you're ingesting tens of thousands of patients worth of records, that's often several thousand records per patient, you can't do it per hand anymore. And so with that, we're coming to ideas around how do we introduce true multimodal data. And so we've assembled a simple pipeline just to test things with, where we have electronic healthcare record tokens, what I started to show you with, where we're now introducing clinical nodes from radiology, for example, and we've started to inject electrocardiogram data, so the actual traces of electrocardiogram. And we've assembled a model and developed a strategy and structure to train this model that I don't have the time to speak about, but you will be able to read soon about, because we believe that this is an open architecture that after training of the large transformer allows us to add new modalities. And that's because effectively we've given up on the standard idea of tokens as discrete units, for those that know about this, and have moved to entirely continuous latent representations of the data. So just to give you a sense of that, we have now different encoders that can take the ECG trace, as you see on the picture, and then basically transform that into an ECG codebook that delivers us this non-discrete continuous tokens, these latent representations of the ECG data, and we can inject that. And just to give you an example of how that looks like, what you see on the left is the predicted mortality of a real patient using just the electronic healthcare record. And you see there's a red curve that tells you at the bottom is 0%, at the top is 100%, and you see the shaded area. That happens if you run multiple simulations of these patients. So you roll out multiple times the model predicting what's happening with this patient. That's just like asking ChatGPT to generate the same, answering the same question over and over. That's what we're doing here, but the rollout is not text, but medical information. And out of that, we can then compute the mortality. Now, what's interesting here is that the patient at the far end of the trace actually dies, sadly. Yet if you just use the EHR, the best prediction you can do is that the mortality at the moment of death is 66%. It's not great for an AI that needs to predict mortality if you die in the moment that you're predicting that they have a 1/3 chance of survival. If you start integrating the ECG and the clinical notes information, then you get a better trace and prediction in the rollout. And in our case, and that's the graph on the right, actually, as the patient dies, the mortality goes up to 100%. So that's fine. So we can use these simulations that roll out what's going to happen to you to predict mortality. We can predict many other things, whether you're going to get pneumonia, whether you're going to get sepsis. We can do prediction of what's going to happen with you. We call that prognosis. But really what we want to know is we want to know how to treat you. What can I do to prevent what's happening to you? And this brings us to the idea that we now need to think about test beds for digital health. We have now this AI engine. We call it Nightingale. You can call it whatever you want when you're building it. But now we want to know, does it work or not? Can we find common rules to do that? Think Olympic Games, different runners running the same race. So we know how good it is. So you know how good the product is, and you just don't have to listen to the marketing. So this idea of crossing the treatment gap is what we call building an AI clinician, a system that reasons about what you may have and what should be done to you. So we want to do an AI system that does more than just a supporting role. And this is where we're really talking about using Nightingale to build agentic AI, a system that suggests do this to the patient and then do this, and if they don't respond, you do that. And to test these systems over the years, we've built, and this is our local hospital, St. Mary's Hospital in London, we've taken hold of a whole hospital ward and basically installed full sensory availability. And what you're seeing here is a clinician, he's wearing the head-mounted camera, coming and visiting a patient. For illustration purposes, I'm not showing you a real patient, I'm simply showing you a dummy that sits in there. But what we can do in this context, we can now actually put not just a camera, but an eye tracker. So we know exactly where the medical doctor is looking. You see the heat maps where he's paying attention. And then you have your agentic AI, the AI clinician making a recommendation. And that's, of course, not a robot, but it's a computer screen. And that computer screen tells you in the middle what you should be doing. And in the 4 quadrants, it offers you different interpretations or explanations why you should do that. And once you do this systematically, and we've done it and run a clinical trial over a year now, where we've established this test bed and then actually trialed it with real patients and real doctors, of course. And to our surprise, we discovered that, for example, doctors did not care about the explanations. They literally didn't look at them. They cared about what was the recommendation, and then they stared into the blank space. Eye tracking gave us that, and they started thinking about it. And then they made a decision where they said, we follow the recommendation or not, or we adjust the dose of this drug as the AI says it, or we move away from the AI recommendation. And you can read all about that. So we can do that. And so what we're showing you now here is how close our model now comes to performing consistently with the medical decisions that patients were treated with in our data. And we're looking at 3 cases: the prescription and dosage of the antibiotic, the antithrombotic, and a diuretic prescription. And you can see that we're achieving often close to 80% coincidence with what the clinicians actually prescribed. And we have evidence, and I can't speak more to that at the moment, that 20% of that mismatch is not because the model is not perfect in reproducing the clinician, but in actually showing what may have been done better than what the clinician did, where the gold standard must not necessarily be the best answer to that. And I'm very happy.
Are you done?
I'm done.
Okay.
To take questions.
Okay, let's first thank Charles. Yeah. Like the last time, if you're here and would like to ask a question, please use one of the microphones there, and I'm monitoring the ones online. Any question for Aldo? Yes, so difficult to see who is going there. Oh, is someone asking a question? Oh, great.
Hello. Well, thank you so much. It was a really cool talk. I think this opens up a very exciting possibility, but it's also like mildly terrifying in a couple of ways. And I'm wondering if you could speak to that. I think the 2 obvious things that come to mind for me are privacy. And I know you said you anonymize the data, but I think it's pretty common to de-anonymize data these days as well. And how willing are patients going to be to share their personal healthcare data with some AI model? And the other kind of terrifying thing is, what if the clinician listens to the AI and the AI is wrong? Who is held responsible in that situation?
Brilliant question. Let me ask backward. So in the papers we published, we actually did a number of controls, experiments, where randomly we make the AI, well, it wasn't the AI, we simply wrote what the recommendation was, and we wrote it so that it was dangerous, right, or not good for the patient. And fortunately, 80% of clinicians picked that up and said, this is not right. And 20% did go along with what the AI recommended, more or less. That's interesting. Now, you saw the young male nurse in that room. That was my PhD student. He is a medical doctor himself, but he played the nurse, or he worked as a nurse for that period. He flipped a coin before every trial. And flipping the coin to head made him say, "Are you sure, doctor?" That coin flip made 30% of doctors change their mind. So when we're talking about evaluating AI systems, we're looking at the human-AI interactions. I'm just showing you that the impact effect of the human-human interaction is large in that space. And that's why we need these test beds, so we can systematically measure that, because before AI in healthcare, there's been very little evidence or work on actually evaluating the performance of clinical decisions per se. In another paper we published, we showed that there's over 500% variation in the prescription of drug dosages in hospital for that specific treatment. It's all published. You can look at that. I'll leave it at that. Now, the challenge with the healthcare data is, I think, sensible. And I think we also need to be aware that different systems arise in different care systems. So in the UK and in Europe in general, it's, for example, forbidden for insurances or employer to use medical information for decision making. And you're covered anyway for life. So no information can change that coverage. So therefore, the attitude towards providing information is different in that sense. Another legal difference that we have, that all medical data, because it's owned by the state, it's the country's healthcare data, so to speak, the country pays for it, not the patient, can be used for medical research and innovation. And so this gives us the opportunity to think about systems that benefit patients. But of course, there's a risk that if the data leaks or the data is abused, that others can then try to infer things about you. That is why Nightingale AI, it's an effort by academic institution, the academic supercomputer, and university hospitals that bring these data together. We are, so to speak, what I call neutral ground players. We have no economic benefit. And the beauty of that, once we've trained Nightingale, you can then access, as a corporate player who wants to build a tool on top of it, to the knowledge that is contained in the healthcare data, but you will never see the training data that we used. And so that's a way of basically removing the commercial interest from the human individuals by putting an AI system in between.
You can take one. Please go ahead.
Hello, Aldo. Thank you very much. Fascinating talk. I think I heard you mention that Nightingale is about a 100 million parameter model, which today would count as microscopically small comparing with others. Is that because the amount of data that went into its training is either much smaller or time series included, highly correlated? What's behind your system scaling dimension magic?
Thank you so much for your question. So, the beauty of that is that we've thrown away language. Okay, I studied computer science because I didn't want to study literature, right? Okay, so the beauty of that is that the tokens, the embedding spaces for numerical, tabular, even image data, and you can look at the large image models out there, they're much, much more compact than those that we need for language representations, right? And so that's why the models can become smaller. As I said, you can get a paper in Nature with a 2 million parameter model. We are 50 times that size. Of course, we know that we have effectively plateaued in the scale size of the model given the amount of data we have. And as we're adding new modalities, ECG, genetic information, that model will grow. But we are at a scale where we can still operate very safely on some 5,000 GPUs and lead this development further. And so thanks to a grant by the UK government's Department of Science, Industry and Trade, we received 1 million GPU hours on Isambard. And with that, we have the compute that OpenAI had for GPT-3, but we hope we can get further than they did. And so now it's about building coalitions around data and in putting that data into Isambard and building a model that can digest all this data.
So let's thank Aldo. And with that, let's work. You can take this.